Our knowledge of genetics has given us the understanding of stuffs like evolution, inheritance, and whatnot. So, wouldn't it be nice if we could model and simulate such stuffs? Well, for this, we need something we call genetic algebra. Now, let's start by an allele. What is an allele? There are different forms of gene which represent a character. For instance, say the color of a flower. Say the allele capital A represents the white and small a the red color. The different combinations of this gives us the color of a flower. Now, this brings us to the first topic, Hardy-Weinberg principle, which says that if you have the frequency of capital A as P and small a as Q, then the frequency of the pair capital A is P square. Capital A small a is 2pq and small a has a frequency of Q square. Now, just as a side note, we need a pair of alleles to represent a character in this case. Now, before proceeding further, let's try to understand what is meant by a basis. In this case, let's talk only about the space Rn instead of a general vector space. We call this set of elements a basis of Rn if every other elements in Rn can be represented as a linear sum of these elements. And it must be linearly independent. In other words, if the following sum is 0, then the value of the coefficients is 0. Now let's come back to genetics. Bernstein's problem plays a significant role in understanding the problems in genetics. To begin with, we start by taking n real numbers or a coordinate in Rn such that their sum gives us 1 and all their numbers are positive. We now take the set of all such set of reals and name it S. We call the vertices of S the basis elements of S, and it represents the different types of individuals in the population. Next, we note that the probability of EI and EJ giving rise to EK and call it gamma IJK or JIK. Now clearly, the following sum gives us 1, as EK must have some parents. Now these all relations give rise to a map, which we also call the evolutionary map, which when applied twice gives back the original operator, and the problem is to explicitly find out all such maps. Evolution algebra helps us to understand the flow of evolution from ancestors to the generations. Here we define the basis as the following. Now here, the basis elements individually represent individual alleles. The product of two alleles is 0 in case I and J are not the same. And in case they are, they can be represented as linear combination of the basis elements. Train algebra again plays an important role in understanding certain problems in genetics. Here we have to deal with a field K and a function, which we also call the weight function. Now we take n elements from K such that their sum gives us 0. Now suppose an element A satisfies the following polynomial. We say that the element A belongs to the particular associated train algebra. In other words, every element of the algebra satisfies this polynomial.